Hello AP Physics students, this is Dr. Buoyancy and this is lesson A.3. We're continuing our unit on fluid dynamics. And in today's lesson, we're going to be explaining why concrete boats and paper clips can float. Sounds like an interesting topic. And then we're going to be able to calculate the density of a rock without actually measuring its volume. Now that sounds very interesting as well. So let's figure out how we can do this using fluid dynamics. So the whole idea behind being able to do both of these things has something to do with what's called buoyancy. And give me a second here because I got to plug my iPad in here before it runs out of power. There we go. So buoyancy is this phenomenon where when you have a body resting in or on a fluid, it experiences a net upward force due to the pressure difference within that fluid. And that phenomenon is called buoyancy. So this lady who's, enjoying her time on her inflatable raft is being held up in that fluid or on top of that fluid by this phenomenon called buoyancy. Now, buoyancy was first studied in depth, most famously by this guy named Archimedes. And Archimedes was a very smart mathematician and scientist, and not in the sense of today's word scientist, but he was curious about natural phenomena. And what he discovered is that when a body is completely or partially immersed in a fluid like water, the fluid exerts an upward force on the body, and he found out that that upward force is equal to the weight of the fluid that is displaced by the body. Let me show you an example here of what Archimedes meant. Okay, so there are three different things that can happen to an object when you immerse it in water or when you put it on top of water. It can either sink, or it can hover, or it can float. And what happens when an object sinks is that this buoyancy force is not as large as the gravitational force on that object. So in this example over here on the left, this object will sink to the bottom because its gravitational force, which is equal to its mass times g, is greater than the buoyancy force that holds it up. And according to Archimedes, this buoyancy force is equal to the weight of the amount of water that is displaced by this object. So what you have to do is you have to calculate, you take the density of the fluid, and you multiply that times the amount of volume of water that was displaced, and that will give you the total mass of the water. And then if you multiply that times g, that's the total weight of the water that was displaced by this object. In this case, though, that buoyancy force isn't as large as gravity, so this object will sink. So in this case, gravitational force wins. Since this object is completely underwater, the volume of water that's displaced by this object is the volume of the object itself. So we would say that the volume of the object, which is V, is equal to the amount of the volume of water that's displaced. And that volume of displaced water we're going to call V sub D. And one other thing that I should get into the habit of doing, especially in this unit, is distinguishing volume from velocity, because in the next lesson we're going to have to use both. So what I should do is I should put these little stems on the top of the V's to denote that those are capital letters, which represents volume. Okay. So the volume of the displaced water is equal to the volume of the object, and that means that the density of the object has to be greater than the density of the water or whatever fluid it's in. So when something sinks, an object sinks, we know that its density has to be greater than the density of water. Right? Something else that can happen is that an object can simply hover in the fluid without sinking or floating. And the technical term for that is called neutral buoyancy, because it's neither being pushed up nor down. But, I mean, a common name might be it hovers. And this is actually what submarines do when they are underwater. They match their amount of buoyancy force equal to the gravitational force. So this is when the two forces balance. The amount of volume of liquid that is displaced due to this object is equal to the volume of the object itself. So we could say that V is equal to VD. Again, let's put those little stems on top. I gotta get in the habit of that. Well, if that's the case, then the density of this object has to equal the density of the fluid. So the only way you can get yourself to hover in water under the surface is to match your density with the density of the fluid itself. And submarines actually do that by releasing and taking in as much water as they need to in order to hover. The third fate that can happen to this object is that it can float. Okay, and something floats if it will hover on the top of the water. So it's not sinking, it's not rising at this point when it gets to the surface of the water. So that means that these two forces have to be equal. The gravitational force has to equal the buoyancy force, but you'll notice that not all of the volume of the object is underneath the water, so it's not displacing its entire volume. That means the amount of water, the volume of water that's displaced is actually less than the volume of the object. Or you can say the volume of the object is greater than the volume of water that's displaced. And the only way that this can be true and this can be true is that if the density of the object is actually less than the density of the fluid. So an object's fate in a fluid really depends on its density compared to the density of the fluid. If it's greater than the density of the fluid, it will sink down to the bottom. If it's equal to the density of the fluid, it will hover with neutral buoyancy. And if the density is less than the density of the fluid, then it will actually pop up to the surface, and part of it will hover above water, part of it will hover, be immersed below water. Now, something to think about here. We've been talking about density so far, but there are some things that float that are actually more dense than water, like concrete. So concrete's more dense than water, so if we had a slab of concrete, it should sink. But civil engineers and civil engineering students across the nation actually compete in what's called a concrete canoe race. But what makes this possible? Even though the density of concrete is greater than the density of water, it still floats for some reason. Well, the reason it happens to float is because not all of it is made of water. Okay, and let's actually take a look at a ship in order to figure out what exactly is going on here. Now, this entire ship is not made out of steel. I mean, everything on the inside is made of air, right? And air is less dense than water. So overall, if you took the average density by taking the total amount of mass and you divide it by its volume, that density actually is going to be less than the density of water overall. So that's why ships made out of steel, made out of wood, well, wood naturally floats anyway usually, but concrete canoes, that's why all these things float, is because they're watertight, which allows them to displace more water than the actual shape of the object would, or the actual thickness of the object would. Okay, so we can actually use buoyancy to also weigh the mass of a ship, or to weigh how much the ship, to weigh how much the ship weighs, I guess. It's kind of a weird way of putting it, but what we can do, and actually this is actually how people in the shipping business actually measure how much weight they have on board, is by using buoyancy to their advantage. So we know that buoyancy is given by the mass of the water that's displaced times g, and this entire thing would be the weight of the water that's displaced, and that has to equal the mass of the ship and its cargo times g. So we know that, oops, and one thing I forgot to say is that the volume of the water that's being displaced is equal to the amount of volume of the ship that's actually under the water line here. So we would calculate the entire volume of this part of the ship right here, and that would give us the volume of water that's displaced. Okay, so we know that this ship isn't sinking, it's not being pushed up, so these two forces have to balance out. And we can divide both of these by g, if these forces are equal, and find out that the density of the fluid times its volume, the volume that's displaced, is equal to the mass of the ship. As a matter of fact, in the shipping business and in naval, in places like the Navy and stuff like that, they actually quote not the mass of the ship, but they actually quote the volume, actually the mass of the water that's displaced by the ship. So you will actually hear about ships being talked about in terms of displacement, rather than in terms of the mass of the ship itself. And that displacement is the density of the fluid times the amount of volume of the fluid that's displaced. So the shipping business actually takes advantage of this Archimedes principle. So as the ship gets loaded up, it gets more and more massive, which means it has to displace more and more volume. And so it has to start sitting lower and lower in the water. So if we start loading the ship up more and more, it may sink so that the water line ends up right here close to the top. Or closer to the top, I should say. So if we load it up. If we take cargo out, then we're going to start seeing the ship come out of the water, so the water line might end up being down here, or maybe even down here. Okay, so you can actually tell how loaded up a ship is by seeing where the water line is on the side of the hull. And actually shipping containers and shipping containers have marks on the sides of the ship that tell the people loading it how much volume is being displaced, and therefore how much mass they've loaded up onto the ship. So that's how you can weigh a ship, or weigh the cargo in a ship without actually measuring, actually putting it on a scale. Okay, let's put it that way. All right. Well, let's. What do we have here next? So let's do an example here. Another example of using Archimedes' principle and buoyancy to measure the property of something. So mineralogists actually use buoyancy to measure the density of rocks and minerals, and they do this by first weighing the rock on a spring scale. And so let's say that a mineralogist has a big rock, and she puts the rock on a spring scale and measures that it has a weight of 1,835 newtons. And then an interesting thing that she does next is that she puts it in a tub of fresh water. So this is a tub of fresh water. She puts the rock in. Whoa, I'm getting a little carried away here. Let's back that up. And then what she'll do is she'll actually measure the spring force again. So the force on the spring scale, she'll measure it again. And this time she actually comes up with a lesser weight of 1,315 newtons. And how does she use this to measure the density of the rock? Okay, well, it turns out that when this rock is immersed in water, not only is a spring force pulling up on it, but there's also a buoyancy force pulling up on the rock. And those two forces counteract gravity. And that's why when you put a rock in water, when you immerse it in water, it apparently weighs less than it does when you weigh it in air. Okay, so we can set these forces equal. So the force of gravity going down is equal to the spring force plus the buoyancy force, both pointing upward. So 1,835 newtons is equal to 1,315. So this is what we measure with it in the water. That's what she measured with it in the air. And you take the difference of those two, and that has to be the buoyancy force. That seems to make sense. Now, Archimedes says that the buoyancy force is equal to the weight of the water that's displaced by this rock. Well, the weight of the rock is equal to the weight, the weight of the water displaced is equal to the mass of the water displaced, which is density times volume, times little g. So the buoyancy force is equal to the density of the fluid times the displaced volume times g. Right? We know the density of water, but we don't know the amount of volume that's displaced. We don't have a way of measuring that volume displaced. Especially since it's an irregularly shaped rock, so we can't use like some sort of geometric formula or anything like that. But what we can do is we know that the volume of the displaced rock, since it's completely underwater, that equals the volume of the rock itself. So that volume of displaced water, we can replace it by the volume of the rock. And we get the gravitation. Well, actually we can figure out that volume by using the weight of the rock in the air. So the weight of the rock in the air is equal to the mass of the rock, which is this term in parentheses, rho times v, all right? That's mass, times little g. So we can solve this for v, and the volume of the rock has to equal the force, the weight of the rock divided by rho, the density of the rock, times g. Okay, well, since this volume is equal to Vd, let's take this volume, let's take this and plug it into here. And what we get is 420 is equal to the density of the fluid times g times the weight of the rock outside of water divided by the density of the rock times g. Well, it looks like some g's divide out there. And so the this difference between the weight outside water and the weight inside water is equal to the rock's weight times the density of the water divided by the density of the rock. It looks like I'm running out of room here, so I actually have to go on to a next slide. So let me rewrite that equation. Okay, now we know that the weight of the rock is 1,835 newtons. So let's rearrange this equation and work to solve it for rho, the density of the rock. And I can flip both of those fractions, take the reciprocal of both fractions, and that will give me 4.37. And if you didn't recognize this, in lesson 8.1 I talked to you about specific gravity being the density of something over the density of water. So this number 4.37 is actually the specific gravity of this mineral rock. So if I want to figure out what the density of that rock is, I just have to multiply 1,000 times that amount, because the density of water is 1,000 kilograms per cubic meter. So the density of that rock is 4,370 kilograms per cubic meter. Okay, now we didn't even know anything about the volume of the rock. We didn't even need to know anything about the volume of the rock, which is really interesting. We just had to weigh it outside in the air, and then we weighed it completely immersed in water. And we took those two readings to actually calculate the density of the rock, which is kind of amazing if you think about it. So that's one way to find density without even knowing the volume of an object. Now, this is where I normally stop, because I usually stop by showing you an example problem. But there is one part of my objective that I haven't explained to you yet. I told you in the objective that I would explain to you not only why a concrete canoe can float, but also why a paperclip can float. Now, a paperclip is made out of aluminum, and aluminum is more dense than water, which means it should sink. And it doesn't have any sort of shape that allows it to displace more water than what its actual volume is, like a ship does. So how in the world does a paperclip actually float? Well, this is another phenomenon. It's not due to buoyancy, but it's due to something that's called surface tension. Okay, so molecules in a liquid are attracted to other molecules in the liquid. Now, if you have a water molecule in the middle of this slab of fluid, or this volume of fluid, then this molecule will be attracted equally in all directions, and so that net force is 0. But when you're on the surface of that liquid of water, then half of that is missing. So there is actually a net force attraction back down into the fluid. So these molecules on the surface don't want to go any farther than they absolutely have to. So surface molecules, number one, are attracted back into the liquid that they are part of. And another thing that results from this is that they're in tension with the neighboring surface molecules. A way to think of this is if you had molecules dotted along the surface here, then there are little springs connecting each of those molecules to keep them from going apart. So if you start pulling those molecules apart, there's this little tension force, this spring force, that actually brings them back together. And those are caused by intermolecular bonds. So how does this allow a paperclip to float? Well, one of the consequences of surface tension is that it will actually exert an upward force on something that's sitting on the surface. So if something is pulling an object down into the water and it's resting on the surface, now notice there's no part of this that is immersed in the water. What's happening is that the surface of the water is bending around the object. So this object isn't actually immersed in water, so there's no buoyancy force going on here. But those bonds, those intermolecular bonds, are being stretched around here, and they don't like being stretched, so they actually are trying to restore this surface back to its original shape. And so those surface molecules will exert a net force that will point in the upward direction to counteract gravity. And if the force per unit length is less than the surface tension per unit length, then you can actually rest something on the surface of the water. So this little water strider in the bottom left-hand corner, if you notice closely, it has very long legs, long thin legs that are in contact with the water. And notice what it's doing to the water. It's actually bending the water, just like this water is being bent right here. Okay. The amount of force per unit length along here is less than the amount of surface tension per unit length that the water can provide. So the water strider actually stays on the surface of the water, and the water strider actually walks on the water. That's also why a paper clip can float on water, because that paper clip is long and thin, so the force per unit length required to keep that afloat is less than what the surface tension can provide, so it will actually stay afloat on the surface of the water, just like this water strider. Okay, now there's some other interesting consequences of surface tension as well that I want to go through quickly. There's another consequence that water shapes itself into a sphere. Remember how I said that the water molecules on the surface of a liquid or a fluid are attracted to one another. Actually, this is more for liquids than it is fluids in general. But the water molecules on the surface of the liquid are attracted back into the liquid, which is why this water bubble, which is actually was probably photographed on the International Space Station, it doesn't suddenly fly apart. And it doesn't fly apart and go in all sorts of directions because surface tension is actually keeping those molecules on the surface from from dispersing. It's also why water shapes itself into a sphere even when it's falling. Now, we typically think of raindrops as being teardrop shaped, but that's not true. Raindrops are actually spherically shaped. They're only teardrop shaped when they are first leaving whatever surface it is that they are permeating through. But then once they get down here, notice that they are starting to become very nice round spheres. So that's one common misconception, is that water is actually, or raindrops are actually spherical shaped, not teardrop shaped. Okay, another interesting consequence of surface tension is that you can actually design waterproof fabrics that are breathable. And this makes hiking and backpacking and skiing a lot more comfortable, because if we didn't have fabrics like this, then we couldn't exercise and sweat without building up a lot of sweat on our skin and making it very uncomfortable and even suffering from hypothermia. Now, the way that these fabrics work is that they are porous enough to allow water vapor, which are droplets that are very, very small. They allow those to penetrate through the fabric, but raindrops and snowflakes that melt make much bigger drops. And the reason that these bigger drops don't disperse and fall through the fabric onto your skin is due to surface tension. That water drop does not want to split up, because the surface molecules on that water drop are attracted back into the liquid. So that's how you can design fabrics that are waterproof and breathable. And another consequence of surface tension is that actually adding detergent to your water when you wash your clothes, or using hot water, actually cleans your clothes better. And part of the reason for that is that those two things actually decrease the amount of surface tension in water, and so that water can now penetrate into the fabric and clean your clothes better. So that's a little bit about surface tension and about buoyancy, two phenomenon in liquids that allow things to float. And I hope that the example I provided to you can help you out with a problem set. When you finish that problem set, bring it by to me, and so I can give you some feedback on it, and I look forward to seeing you soon. Bye.